Here we have a light bulb. Let's see what we can learn about light by drawing some pictures of light coming out of a bulb. Maybe we start with a typical example of an elementary school drawing. This doesn't convey a lot of meaning. Instead of just using lines, let's use arrows to indicate that the light keeps going in straight lines forever. Also, let's make sure that we send the same amount of light in all directions. Now our bulb has a friend. The left one is a 50-watt bulb, the new one is 100 watts. The bulb on the right looks brighter. How can we show the difference in brightness in our drawings? The wattage represents the rate at which the bulbs use energy. I am going to assert that the bulb that is using twice as much energy creates twice as much light. In my drawing, if I happen to draw 8 lines coming out of the 50-watt bulb, then I should draw 16 lines coming out of the 100-watt bulb. The actual number of lines I draw is arbitrary, but the ratio of the number of lines should align with the wattage ratio. As we saw, the 100-watt bulb looks brighter when they are sitting next to each other, but is that always the case? The dimmer bulb can look brighter if it is closer to you. How do we account for that? The number of lines coming out of the bulbs is related to their absolute brightness. That never changes. However, the number of lines that would get into your eye will change as you move toward or away from the bulbs. The relative brightness of the bulbs has to do with the distance to the observer. How can we test this idea? Here we have 2 blocks of canning wax that are banded together. You notice how the top one is brighter than the bottom one? There's a strip of aluminum foil in between the wax blocks that acts as a mirror. The top block is brighter because it is being bathed in the light coming down directly from the ceiling. The bottom is dark because it is only lit by the light bouncing up off the floor. This rather primitive tool is actually very good at measuring relative brightness. Notice what happens as I move the bulb toward and away from one side. Here are 2 different bulbs on either side of the detector at equal distances. Notice how much brighter the right-hand side is? This makes sense with our model. The 100-watt bulb is producing more light. As we said, the absolute brightness of a bulb is fixed, and the lines that leave the bulb continue out forever. But they spread out. The density of the lines changes. The further you go out, the less dense they are. We can define the density as the number of lines per unit area. The number of lines is related to the wattage, but what is the area that matters? In my drawing, the brightness on any given red circle would be the same. Different circles have different radii, so we might think that the relative brightness of a bulb would decrease as 1 over r. It doesn't. Our drawings are misleading because they are constrained to the plane I'm drawing in. Real light bulbs are 3-dimensional, so are the light rays. My red circles actually represent the surfaces of spheres. So, do you know how to find the surface area of a sphere? Here's a sphere. It's an orange. This is a particularly useful sphere to measure the surface area of because it comes off. I'm tracing the thickest part of the orange a few times on my paper. As I peel the fruit, I'm placing the pieces into the shapes I traced. It's a free-form puzzle. Let's speed this up. So, the area of each of these circles is pi r squared. I filled up 4 of those circles with my peels, so the surface area of a sphere is 4 pi r squared. That means that the relative brightness of a bulb should not go down as 1 over r, but 1 over r squared. Can we check if that really happens? Of course we can. This is a LabQuest interface, and I have plugged in a light sensor that measures the intensity of a light source in a unit called lux. You can see that the value changes as I move the sensor toward or away from a bulb. Let's do this in a very controlled way. The room lights are off and I have a meter stick laid out on the table. As I move closer to the bulb, I can record the brightness at several different distances. Here's the data I got. I can ask LoggerPro to draw me a sample 1 over r squared line as a reference. Look how close our data is to the expected shape. This is compelling, but we need to see this in action. Let's go back to the wax blocks. Suppose I'm a certain distance away from a 40-watt bulb. How far would I need to be from a 100-watt bulb for them to look the same to me? If the brightness on each side is the same, that means the wattage over r squared on one side has to be equal to the wattage over r squared on the other side. Let's try it. There we are. I'm looking at the top of the blocks, which is in line with the centers of the bulbs. The 40-watt bulb is 10 centimeters away from the wax. We can solve for the location of the 100-watt bulb. We get 15.8 centimeters. Going back to my ruler, I see that the center of the 100-watt bulb is at 28 centimeters and the wax is at 12 centimeters. So that's a distance of 16 centimeters. The percent difference between our prediction and the actual result is only 1.25%. Not bad at all. Now that we are confident that this idea works, let's take it out for a spin and see what it can do. We will set up the balancing game again. Let's put a bulb on one side of the wax blocks, and on the other side, we will put the sun. We know the wattage of our bulb and the distance from the wax. We know the distance to the sun, it's 150 million kilometers. Next time you go to the grocery store, buy some canning wax and measure the wattage of the sun.